Our last question, 14.6, is asking us to do a two-way mixed design ANOVA. So what that means is that we have taken all of our subjects and split them into two groups. So instead of just one group of subjects that all belong to the same population, we've got two groups. So they could be males and females, graduates and undergraduates, a yes group or a no group, whatever the case may be. And we want to compare these two groups of subjects across a repeated measures situation. So across 3 trials of something or 2 trials of something. In this case, addition, subtraction, and multiplication. So the same subjects from the 2 different groups across 3 or however many repeated measures is a two-way mixed design ANOVA. Question 14.6 is asking us if having or not having a hand calculator affects one's ability to do arithmetic. So Howell chose 5 of his daughter's classmates who did use calculators and 5 who did not, then gave them 3 10-point math tests to be calculated in their heads. For this question, we are to test for differences in math ability between children with and without calculators. So we have 10 subjects that are broken into a yes calculator and a no calculator group. And then there are 3 math tests where the subjects all completed a 10-point addition test, a 10-point subtraction test, and a 10-point multiplication test. And these are the scores out of 10 for each participant on the 3 tests. So, like with all of our ANOVAs, the first step is to calculate our sums of squares total. So we take each of the scores, subtract it from the grand mean, square it, and sum it up. We get a sums of squares total of 167.87. Next, we're going to calculate the between subjects sums of squares participants. Now to do this, we take each of the subject means and minus from it the grand mean, square that, and then sum them all up. Then we take that sum and times it by I, which is the number of treatments. So there's addition, subtraction, and multiplication, so that's 3. We work that all out, and we get a sums of squares participants for between subjects of 67.2. Now, to calculate the between subjects sums of squares groups, we're going to take the 2 big group and subject means. It's the mean that's both for groups and subjects, so 4.87 and 7. And minus from each the grand mean, square each of them, sum them up, and then we're going to times them by small n, which there's 5 in each subject group, so 5, and times it again by I, and there were 3 conditions. So we work that out, and we get a between subjects sums of squares groups of 34.132. Okay, now for the error term for the between subjects group, the sums of squares within groups. To calculate that, all we do is take the sums of squares between subjects of 67.2 and subtract the sums of squares groups of 34.132 to get a sums of squares within groups for the between subjects of 33.068. Now for our within subjects calculations. The first is the sums of squares within subjects, which is pretty easy. It's just the sums of squares total, which was 167.87, minus the sums of squares between subjects, which was 67.2. That gives us a within subjects sums of squares of 100.67. The within subjects sums of squares takes the test means and minuses from them the grand mean, squares them, sums them up, and then we multiply by n, which is 5, and by g, which is the number of divisions of subjects, which in this case is the yes and no subject groups, so that's 2. We work that out and we get a within subjects sums of squares subjects of 66.47. To calculate the interaction, first we have to calculate the sums of squares cells. To do that, we take each of the group means and minus from it the grand mean, square it, sum them up, and then multiply that by n. So we get a sums of squares cells of 123.85. Then to get the sums of squares interaction, we take the sums of squares cells that we just calculated and subtract the sums of squares subjects and the sums of squares groups. And we get a sums of squares interaction of 23.248. Finally, to get the within subjects error term, we take the sums of squares within subjects of 100.67 and subtract the sums of squares subjects of 66.47 and the sums of squares interaction of 23.248. And we get a within subjects sums of squares error of 10.952. We have 8 different degrees of freedom to calculate, and I'll let you go over these yourself. I won't go over them here. We're calculating 3 F-scores. One for the between subjects groups, so the calculator versus no calculator group. One for the math subjects, so the addition versus subtraction versus multiplication tests. And one for the math by group interaction. I looked up the critical F values for each of the 3 tests, making sure to use the correct degrees of freedom error. And it turns out that each of the 3 F values is significant. So our 2 critical values are shown in red, and each of our F values in purple is further away from the mean than the critical value in the critical region. And so we can reject the null and say that each of the 3 F tests is significant. If we're going to write up some nice sentences at the end of our exam question, we would say that overall, the calculator owners performed significantly worse than the non-owners, while there was little difference between the 2 groups in the addition grades. This trend was especially apparent on the multiplication subtest. Next, there was a significant F overall for the 3 math tests, with the children performing better on the addition test than the subtraction test, and better on subtraction than on multiplication. Finally, there was a significant interaction effect between the math test and the calculator groups. While the children that used calculators did progressively worse on the addition, subtraction, and multiplication tasks, the children who did not use calculators performed significantly better on the multiplication task. So, to conclude, if Howell wanted his daughter to be able to perform multiplication in her head, maybe he shouldn't have bought her that fancy calculator.